control now will put into that.
Unfortunately, I can't ask them. Oh, no, you don't need to see my presentation. How do I get the chat back?
How to get the chat back?
Can I get the whole window back?
The full one? Yeah, if you press escape, you can get under the chat there. So the mouse Is anybody listening on WebEx?
Yes, we muted them because somebody was talking in the background.
If you are listening on WebEx, can you go to the chat and let us know that you can hear us? Thank you.
Okay. Well, at least 2 people can hear and see this, so I'll go ahead and start. Alright. So, this is our Python session in the NOAA modeling fair. I'm the session lead, Trahan. You will also hear from Todd Spindler, Tim, and Deanna Spindler. So here's our 4 talks. I'm going to be giving this intro talk. I'll tell you what Python is and what it isn't. Todd is going to show you how to read some of the NCEP data sets and some observational data in Python. NCEP will show you some fancy videos and images of the ocean underneath hurricane. And Deanna will show you time series data analysis using fancy statistical analysis tools. Alright, so you'll find all of these descriptions of Python online. This first one is part of a long essay by someone on python.org. I don't have 4 hours, so I'm focusing on these words. Python is interpreted, object-oriented, high-level, dynamic, glue, and ecosystem. So let's do Python is first. Now, when we say that some language is something, there's generally 2 categories of languages. The first is languages that have a formal standard by some international standards body, usually the International Standards Organization or IEEE or IEC. And so, for example, you cannot say that your Fortran 2008 compiler is a Fortran 2008 compiler unless it's compliant with ISO IEC 1539-1-2010. Another kind of language standard is proprietary standards. For example, Microsoft makes Visual Basic, and you can't call your product Visual Basic unless you are Microsoft. Python is neither of these. There is no one Python language. Instead, it's a list of recommendations. There's a reference implementation, CPython, which is the implementation you'll get from python.org. Generally, if you download Python, it's CPython. There are other implementations of Python. A lot of them try to mimic CPython. Some of these are not Python implementations in and of themselves. Instead, they are packages that sit on top of Python, CPython to improve it. I'm going to focus on the first 5. I have not used IronPython. It's worth mentioning because if you're in love with Visual Studio, IronPython is Python fully integrated into Visual Studio. Now I'll talk about high-level. So there's high-level languages and there's low-level languages. So let's take an example where you have an array A and an array B. We want to add them element by element and store the result in an array C. So I have 2 examples of low-level languages here. And you can see in a low-level language, you have to describe each step of the process. So I have a loop over j, a loop over I to go over the 2 dimensions of my 2-dimensional array, and element by element. I add the element of A to the element of B and put it in C. That's how a low-level language works. You have to specify every step of the logic. With high-level languages, it works differently. There is some amount of abstraction present that hides all of those details from you. So in these 4 languages, that's how you add 2 arrays and store it into a third. Now, notice that Fortran shows up in both. That's because a lot of these high-level languages can be used as low-level languages. Pretty much all of them, for that matter. Python is the same way. You can use it as a high-level language. You can use it as a low-level language. Now, CPython is a very slow way to use Python as a low-level language, but there's other variants of Python and some stuff you can put on top of CPython to make that more efficient. Now let's talk about interpreted languages. So I'm going over 3 categories of languages here: compiled, interpreted, and just-in-time compiled. Compiled is what most of the software on your computer does. So let's say you have some line of code, I equals I times 3. The first step in a compiled language is to compile it. It becomes assembly language, which is even lower level than low-level languages. It has each individual step as detailed as the chip needs, except expressed in a human-readable form we call assembly language. And then next it runs through an assembler to create what is called machine code. Machine code is the stuff that you put that goes directly into your processor, and there's a little piece of silicon inside your laptop to do the actual computation. You can't run anything on your computer until it's been converted to machine code and sent into that processor. So ultimately, however you run Python or Algo, you're going to have to run it as machine code somehow. So that brings us to interpreted languages. Interpreted languages essentially have a virtual machine and a real machine. So you take your I equals I times 3, you compile it to bytecode, which is this fake virtual machine code. And then you send it to something called a virtual machine, which reads through, and every one of these instructions from the bytecode generally gets converted to tens or hundreds of instructions in machine code. It just occurred to me, I'm not going to see your chat. Okay. Let's put this down here somewhere. There we go. Alright, so for every instruction in your virtual machine, it corresponds to tens or hundreds of instructions in the real machine, which is why interpreted languages tend to be much slower. And that is why just-in-time compilation is invented. This has a third step. So first you take your I equals I times 3, and you turn it into bytecode for a virtual machine. And then that virtual machine compiles it as it's running to machine code for the local machine. Now that compilation, so as an example, let's say you have a loop that sorts a whole bunch of arrays. So you have some sort function that's run 100,000 times. So instead of having to send it through this virtual machine, where it results in spending 20 seconds sorting arrays, you can instead compile that function inside your virtual machine straight to machine code. And anytime you want to run that sort function, you're running the compiled version instead. So Python is actually multiple options here. The reference implementation CPython is purely interpreted, which is why it's so slow. Just in time, there's 3 options for this that I know of. Python compiles to the Java virtual machine, which is widely used for just-in-time compiled languages. The disadvantage of Python is that it's essentially a completely new Python from the ground up. It doesn't share anything with C Python other than the pure Python code. So PyPy is an attempt to make a just-in-time version of C Python. Numba isn't a Python implementation of its own. Instead, it sits inside C Python. You go through and mark certain functions as being compiled dynamically at one time. And then Python is kind of compiled Python. It's really just a Python to C converter. It's widely used to make Python wrappers around C or Fortran libraries. All right, now we'll talk about dynamic. So there's many aspects of Python that are dynamic, and I don't have time to talk about all of them, so we're going to go over dynamic typing. So to explain it, we'll need an example program. So this is your first Python program. You see up here, I'm setting two variables, A and B, to the numbers 1. Notice that I'm not declaring A and B. In some languages, I'll have to say there's an integer variable called A. Not in Python. Variables just float into existence. In the next line here, I'm printing a string. So everything green here from the double quote to the next double quote is the string I will add 1 and 1. Print is a built-in function. You don't have to declare it or get it from anywhere. And it just sends the text to the terminal. So print I will add 1 and 1 just sends the text. Next, you define the function. Notice these two lines below the def are indented. Python uses indentation to define scoping. So the function is def plus this result line and the print line. But when we get down to this line is no longer in the function. So we're defining a function print x plus y. It defines a local variable result that is simply x plus y. And then we're printing a string here. Now this is an F string. It's a way to embed variables or calculations into a string. It simplifies your code quite a lot compared to just converting results to a string, appending it, and so on. So you can see here, first thing I do is embed the value of result, and then just for good measure, I recalculate x plus y. Now here, all we've done is define function. We haven't called the function yet, so all it is a function sitting in memory somewhere. So we have to call the function, and here I'm calling the function. I'm giving it a and b. So the value of a, that's 1, and b, which is 1, go into x and y. Result is 1 plus 1. And here x plus y is also 1 plus 1, so you end up with 2 equals 2. Now that's correctly written Python. Let's suppose we replace b with apple instead of 1. You cannot add 1 and apple in Python. It's an error. So once Python gets to this line where it tries to add 1 and apple, it'll abort. It won't know that it has to abort when it reads the file because it does not know that x and y have to be the same type. All it knows is that they're variables being passed in. That's dynamic typing. Static typing is when you define the type ahead of time, like this. This is Python with static typing. So you can see x int, y int. So that means when anyone calls this function, it has to pass in 2 integers. So as soon as Python, when it's reading the file, sees this line, it knows we're passing an integer and a string into a function that wants 2 integers.
This is doing infinite memory, it's just this time.
Yes, so this would be the step that compiles the bytecode. It'll scan through, it'll see that you're sending the wrong data types into that function, and it'll abort. Whereas with dynamic typing, it'll scan it, it'll compile the bytecode, it'll run it, and it won't know there's an error until it gets to result equals x plus y. And in a little program like that, it doesn't matter because it'll take a microsecond to get there. But you may be running a program that takes a half hour to get to that error line, and you'll have to run it again for a half hour to debug the fix. That's how static typing saves you. And you may be wondering, why would you ever use dynamic typing when it causes such errors? There's a lot of power in dynamic typing. In this line, result equals x plus y. I don't have to know what the data types are. A, B, C string plus D, F string in Python, that becomes A, B, C, D, F. Add two integers, you get two integers. This is a list of integers, 1, 2, 3, another one, 4, 5, 6. I add them and append them. So there's many, many data types in Python, and you can define more, and you can give each one a way to add stuff. To add my circle to my other circle to make a bigger circle. And print x plus y, it doesn't need to know you defined a new type. As long as the type knows how to add itself, then print x plus y automatically works. Now, there are statically typed languages that have solved this problem. There are ways to do stuff like this with statically typed languages. But Python being dynamically typed doesn't have to find another way to solve the problem. And you do have the option of putting in static typing where you need it. Alright. Glue and ecosystem. We'll move on to this next. So you'll see all these claims of these magical things that you can do with Python. Generally, anytime you need to do something with Python, you don't have to write the code yourself because other people have written it at least 5 different ways that are all widely supported as libraries that are developed by many people. In this sense, Python is an ecosystem. You have many options available. Those options constantly are being updated. Some of them may die off. There may be new ones. Some of them will take hold and be available for years and years. And of course, you have many versions of Python. There are many advantages to this. You don't have vendor lock-in. If you don't like C Python, you have plenty of other options to choose from. If you don't want to use some parser generator, you can use one of the 63 other widely used parser generators written in Python. Now, it isn't entirely correct to say that Python does these things, because for the most part, these packages are not written in Python. They're in C or CUDA or C++, Fortran or whatever. And Python has wrappers around them, frequently using Python to implement it. There are some packages that are written in pure Python. They'll use something like Numba or Python to speed up things. But the fact that most Python packages are not written in Python is an advantage, not a disadvantage. It's easy to plug other stuff into Python. That's why it's commonly called a glue language. It's not like Fortran where you have to jump through hoops of fire to plug it in. So next we'll talk about object-oriented. This is for full 1 semester classes in a computer science degree to explain this, and I'm compressing it down to 3 slides. So here goes. Here's what you do without object-oriented programming. Let's suppose I'm keeping track of colored circles. My circles each have a location, X and Y, a radius R, and for color I'm defining a red, green, and blue channel. And I have my 2 circles here, one yellow one and one blue one, that in this case have the same size, but a different location. There's all these things you might want to do with 2 circles, like get the minimum covering circle or get the hue. And if I want to know the minimum covering circle, I have to know where to get the x, y, and radius of each of the 2 circles, and I have to know to pass it in to minimum covering circle. So if someone wants to go through and change how circles are stored, they have to go through all of these functions and all of the code that calls the functions to update it to have a new way of defining a circle. So what you really want to do is separate the interface from implementation. To separate how you interact with the circle from how the circle is implemented in your code. Object-oriented programming is one of the ways to do that. So this relies on 2 things, an object and a class. An object is just a data type that stores some data and stores ways of interacting with the data. You can see I'm defining a circle, and circles contain all of this stuff, and these are the things you can do with a circle. This is a class definition. It is a kind of object. Now, when you go to work with the actual objects, you won't make what is called an instance of the object. In the instance, here's my blue circle hidden inside here. There will be the X, Y, the radius, and the red, green, and blue channels. The little floating point number is hidden inside here that I don't even need to see. Now here, as the caller, as someone who's interacting with a circle, all I need to know is that I have a circle, and these are the functions that I can use to interact with the circles. Some of them take another circle as an argument. Like if I want the distance between two circles, I have to give it another circle. This is part of the interface, but I don't need to know how the distance is computed or how the two circles are stored. That's your separation between interface and implementation. This solves a lot of maintenance issues in software packages. You don't have to go to a million places to change the storage method for your circle. And there's a million other advantages to object-oriented programming, and if I had 4 hours, I'd explain all of them to you. But one of the nice things about Python is that you don't have to make everything objects. You can do pure functional programming, or even list-based if you want to. Object-oriented programming is optional in Python. Let's see. Running Python. Okay. How am I doing on time? 6 minutes? Okay. So this part is only about 30 seconds. So the people after me are going to show you fancy things in Python, but first you need to know how to run Python. So there's generally 3 ways to do this. There's interactive ways to run Python. There are a million ways to do this. I'm going to use one called IPython because it looks nice. And I don't have to open some expensive GUI. So it does take about 10 seconds to start Unjet because the file system is closed. So we're waiting here for IPython. And soon it's going to give me a prompt where I can type some Python code and it'll go and give me the result. And right here, 1 plus 1, 2. Run math import star. And let's use a more complicated way of doing 1 plus 1. Cosine of 0 plus sine of pi over 2. I'm remembering right, 2. And you can also do comparisons. 1 plus 1. Apparently 1 plus 1 cosine 0 plus sine pi are the same. You can't compare not a number to not a number because they're not numbers. I can ask if 1 plus 1 is 3, and indeed it is not. Hello world. Now this is one way to run Python. And with fancier tools you can show graphics and we'll see some examples of that, but not quite as interactive because we don't have a spectacular network connection here. The other way to run Python is non-interactively. So here's an example Python script. Again, it takes 10 seconds to load things on Jet. Alright, here we go. So, first line in any Python script on Unix is the shebang line. In any interpreted or shell language, you're going to have something that tells it where to get the interpreter. Here, import math. Python has 1 million packages, and you can get 1 billion more online. Package contains all sorts of convenient functions. The math package is one of the core packages you get when you download Python, and it contains mathematical routines and constants. And you can see here I'm calling the cosine function from the math package, the sine function from the math package, and I'm using the pi constant from the math package. And if I run this, dy 1 plus 1 is 2. Now another way to run Python So what I'm doing here is I'm running Python non-interactively. I'm telling it to run this command, and it tells me I have a syntax error. No, it's because I was using the wrong version of Python. Sorry, these Python F strings don't exist until Python 3.6, and I was using 2.6 when I typed Python without 3.6. And I don't think I have time to go over Python 2 versus 3. So do we have any questions? Oh, what about people on the call? Oh, I see a question.
So this is all open source. It's sort of like R. You can download it and use it.
Yes, so there are some closed source packages you can add to Python, but by and large, everything is open source. I mean, there's nothing stopping you from distributing your own closed source package for people to use in their Python programs. But Python itself is open source, and it has a license that ensures it will stay that way.
Is Python written in C++? Yeah.
No. C Python is C, I'm pretty sure.
That's why it's called C++.
No, I don't think it's true. So it also depends whether you're talking to individual libraries. That's all underlying transport things. You don't see that.
Oh, someone asked, can we use SSH? That's what I'm doing here. Not here. Hold on. Oh, here. I'm just SSH'd into NOAA's cluster running Python. There's also Python packages for running SSH. Not sure what you want to do, but yes, you can SSH in, run Python. If you have X11 and the appropriate Python packages, then you can do graphical things through SSH. And if you're interested in SSHing from Python, there's many packages for doing that.
What exactly is Jupyter?
Jupyter is Mathematica or MathCast. It's a notebook system. Very simple. So it's a server-based notebook system using a web browser.
It's like R++.
Yeah. In fact, it's great. In fact, the R in Jupyter is R. Julia, Python, and R. That's what freeway they decided to do. It's extended to 100 languages.
Okay, we have time for one more. Yeah. No, you can get it for Windows and Mac OS. If you have any Unix machine, you generally already have Python. But with Windows, you have to download it, and of course, there's multiple options, including one. So, I don't know where phone is on this keyboard, but I have my list here. Iron Python, if you're especially fond of Visual Studio, is a good option for Windows fanatics. You can get it for Android, iOS, pretty much anything you want.
So we just kind of compile blocks like classes and functions, but not like real good.
I'm actually doing everything on the fly. So it's grabbing as much as it needs to move forward, compile that, and then deliver it back.
I think the JVM works on a subroutine basis. I don't know how the other ones do. There's no Python standard for how to do the just-in-time compiling, so people do it how they do it. And you have 3 options for just-in-time compiling with Python, so take a pick. And if you use the JVM, then you have a million JVMs to execute it. Right, I think we're going to have to move on to Todd's presentation. There we go. Oh, let me get off of chat. Shouldn't leave yourself logged in. And someone asked what SSH client I'm using. I'm using PuTTY.
Okay. The subject of this part of the tutorial is reading scientific data sets in Python. I'm Todd Spindler. I work here at EMC. I'm an oceanographer with the verification group. Been responsible for working with ocean models since about 2005. We have been doing large-scale ocean modeling since I first came here. And we started with an Atlantic model, then graduated to a global ocean model of high resolution, which is currently running. Every time we've upgraded the model, we upgrade resolutions, or we upgrade, in this case, from a regional to a global model. The data that we generate in the model, it becomes mountainous. We need to be able to see what's going on in the model, so visualization is important. Validation, taking the model results and comparing them with observations becomes important, and the size, the amount of data that we're talking about is massive. Visualization, traditionally, is a resource-intensive process. You can take a very powerful workstation, put a nice data visualization package on it, and you got a very slow workstation. In order to be able to do these validation efforts, we find ourselves in something of a race between what we need and what we can do. So we started with MATLAB back in the early 2000s, because that was the best commonly available interactive visualization system with high-end merits. And it worked fine for the Atlantic model for a number of years. Graduating to the global model, we found that our desktop simply couldn't handle the amount of data. So we had to shop around for more and better ways to do things, which, as time goes by, we settled on Python for a number of reasons. It's like we've seen here, it's a very clean syntax, easy to program, fairly easy to learn as long as you don't get into the intricacies. There's a rich suite of operators, methods, many highly extensible and advanced capabilities come with the language. Memory management, parallelism, you can do MPI in Python. You can pretty much, as Sam said, it's a glue. You can pretty much do anything you want in it. But at the end of the day, you do have to be somewhat careful. It's an interpreter, and it doesn't always go as fast as you want. You can make it go very fast if you know various methods. But getting back to what we needed to do, forgot to mention, it's also cost. Just going to mention very quickly, we started with MATLAB. MATLAB is an expensive system. License is expensive. Python is free. And the Python modules and libraries you can extend it are all free. You can buy systems or modules and things, they're available. But usually there isn't a need because the community available software is very high quality and continuing to improve on a daily basis. And a number of these things and systems are well supported by the community, industry, and the government, including DARPA. And all of this really came down from the fact that we have so much information and data we need to look at. We need to process this thing. So what I want to do here is give you kind of a brief tour of what we do, or what I do. It's a very basic task. Start with a data set. Go as quickly as you can to produce a picture from that data set, a visualization. This is going to be a 2D visualization, a surface view. In as few steps as possible. So 3 different data sets. I'm going to mention before I get into the software code that first off, we're working in Python 3. Sam mentioned there's a 2-3 debacle going on. Python 2 is on the way out the door. Python 3 is the future. We're also using something called Jupyter Notebooks. Anybody who's ever played with mathematics is familiar with notebooks. These are slides extracted from. But the website that I mentioned earlier and mentioned here has all of the notebooks which can be viewed. You can download them with the data sets and play with them. The 3 data sets I'm talking about is NetCDF, the Network Common Data Format, Open Standard, very common in the scientific community, gridded binary, or a very long name, General Regularly Distributed Information in Binary Form, defined and controlled by the World Meteorological Organization. It's older than NetCDF. It is very efficient, but it can be somewhat difficult to work with, typically requiring things like external table definitions and so forth, whereas NetCDF is not getting into the details. The third one is Buffer, Binary Universal Form, for the representation of meteorological data. Buffer has been around to give us a compact way of dealing with large amounts of station observations, typically time series data. Has been extended here to do other things like satellite plots and so forth. NetCDF is both input and output oriented for models. Models generate NetCDF, models read NetCDF. Grid is typically output only. Software is typically input only. Let's start with NetCDF. You can read a NetCDF data set using any of the 3 commonly available libraries for Python. These are all extensions to the basic Python system. NetCDF for Python was the first one. X-Array is newer. Video was one off to the side. It's a Unidata system, not commonly used. I'm going to work with a global RTOS, that's a real-time ocean forecasting system, NetCDF data set. It's a fairly small version. We have much larger ones. I didn't want to very many. Plot a parameter, in this case, sea surface temperature, and select off a subregion around Hawaii. Okay. Thank you. X-Array, like all the modules, is easily installed if you have a distribution, if you're doing it for your own systems and laptops. Pip, Conda, or any package manager, talk to the various repositories, whether by python.org or wherever your distribution comes from. Or you can download the entire package and install it with this utils. We begin now going into the Python, and you import the required libraries. I'm looking at the screen. Whenever you begin a Python project that involves more than just the base standard, or even the base code, you have to begin by importing what you need. And you don't have to bring in what you don't need. In this case, I need some graphics, I need some numerics, and I need to do some mapping, an extension to the graphics. Matplotlib is the basic graphics library that most people use in Python. There's a number of other options, but it's extremely common. X-Array or extended arrays. These are n-dimensional labeled axes arrays. It's a very powerful, fairly new module. Tries to do a memory map of NetCDF itself so that you can open a file and actually see the data structure. Cartopy is cartography for Python. It's a new system for developing and managing map projections in a very straightforward fashion. We begin by opening the files as an X-Array data set and display the metadata. Here, the command is xarray.openDataset. So you got to tell it, you give it a file name. In this case, it's an RTOS file. It's a global surface file. I'm reading off what the various elements mean. It's a nowcast. That's what the N000 means. It's a daily prognostic file. It has a certain number of surface variables. We have a daily diagnostic file as well. And then we got a bunch of 3D files, which are massive, and they have all the volume of the ocean in each one per parameter. What's important about this is that you save it to something called dataset. Now, that's not a variable anymore. It's an object. As Sam mentioned, I've instantiated a data set, X-Array data set itself. Let's call it a data set. It comes with a lot of built-in capability. When I do that, if I hand it the option of decode times, then OpenDataset will automatically decode the datetime values from the internal NetCDF representation. Anybody who's played with the NetCDF, datetimes can be a little tricky. This takes care of that and turns it into Python datetime objects. Very easy to work with. I'm using a local data set here, the local file. You could replace that file name with the URL to Threads or OpenDAP data server, and it pull it directly to your computer without any more intervention needed. It will come in and it will map itself just as if you were working for a local file. You can also subset within our data set. You just type the name of the object, data set. This is what it returns to you. Now, there's a few things here you want to watch. You got the dimensions at the top. You've got the overall dimensions of the largest size of the file, because you can have a number of 2D and 3D, 4D and 5D objects mixed together, but overall, these are the dimensions that are being used. We have one layer. We have one model time. We have 4,500 columns, 3,298 rows. Fairly big for a surface data. The coordinates are the same as for empty. We have an extra date parameter, one layer. X and Y are to reference integer indexes into the array, but we also have latitude and longitude defined. The data set can now be mapped onto a globe with a proper map projection. The variables are velocity and the horizontal U and V, meridional and zonal, sea surface temperature, sea surface salinity, layer density, and then finally some metadata that comes along from the work that they did with this region. There's an extra date field. We can get rid of this just simply by telling dataset.drop. That's the dot method is the object-related version of a function. We can also just simply say delete data set. In square braces, the name of the parameter. Now there's a quirk in the global RTOS data set. The bottom row of the longitude field is unused in the model and is filled with junk data. You don't want to use that. I'll subset it to get rid of it. What I do here is I take the data set .sst, I'm now period referencing the parameter. I could say dataset square brace SST in quotes, but I don't need to. Square braces now, to the right of that, is indexing into the array. I'm pulling one array out of the collection of arrays that are in that dataset. I'm beginning by indexing on the first layer, there's only one. I do that to get rid of it. Then I tell it to go start at the top and go all the way down to the next to last row, and then stop, and then all the columns. Python lets you shorten that a bit. If you have any time when you're doing indexing and all you have is comma, colon, comma, colon, comma, colon for all the extra dimensions, just stop at the last column, drop some square braces. Python assumes it'll be full colons for the rest. It's a nice little shorthand. When you subset the SST, you're not just talking to the SST data array, you're talking to its coordinates as well. They can be multidimensional just as much as the data set itself. In this case, when I subset that and tore the row off that, the latitude and longitude arrays also were subsetted automatically, keeping everything coordinated. And when you look at it here, you see that the SST array at the top, you'll see it's now 3297 by 4500. And everything else has been dropped. All we have now is the model time, which is 2018 August, the latitude and longitude values, and some metadata. We can take a quick look at that without having to go through all the mapping, just simply by using some of Matplotlib's built-in graphics features. You begin by defining a figure. I imported Matplotlib in the beginning, gave it the PLT shorthand. Everything in Python uses namespaces. You bring something and you give it a unique namespace, and all of its methods now can be distinguished from the main Python calls and any extra calls. It prevents namespace, name collisions. Load a figure. IMShow, it's an image show. Give it the name of the variable, SST in this case. Now I gave it the name of the object. Notice it's ignoring the latitude and longitude subarrays. I give it a color map. Now this comes in, if you notice it's upside down. That's how the model stores the data. The latitude array is similarly flipped in storage so that once you put the latitude, longitude, and everything together, the mapping subroutine figures out that how the world's supposed to look. Longitude values are a bit odd if you look at them. If I print them out, you'll notice they go from 74 to 434 on a globe defined 0 to 360. We had to rotate the globe slightly because if you look at the grid, it's a little strange. North of 49 latitude, we have what we call polar patch. We had to get rid of the North Pole. North poles, any kind of a polar arrangement in your grid for an ocean model is not easy to deal with. It's singularity, and the model can't handle that. So we'd have to match around it, remove it. In this case, we defined a subgrid, or a special grid called a tripolar that actually has 3 poles, 2 in the north and 1 in the south. We don't worry about the one in the south, it's over land. The one in the north, we're able to move them over land, so we don't have to deal with them. But it does make for a very strange looking northern grid. Now we set up the figure plot the SST field. In a Mercator projection, using that Partify module we loaded, and we're going to let that handle the projection details. We're going to tell what we want, not have to worry about latitude limits, longitude limits, all the details. This makes it very simple. And we're going to let X-Array itself decide how to present the data to us. Now that's one thing that objects are pretty good at. X-Array comes with a great deal of math and numerics and statistics and graphics. It hooks together with Pandas, which you'll hear about later, and they kind of play nice together. X-Ray is in fact smart enough so that when you're plotting, it'll figure out the color map it wants to show you. It may not be what you want to see. If you have a color field or a field that happens to cross 0, it assumes you're going to want a diverging color map, a bicolor, red, blue type of thing. If that's not what you want, then you override that by specifying your limits in the new color field. In this case, this is the full setup for the field. To begin with figure plotting, set the figure up. We have to load an axis now onto the field and tell it what projection we want to see it in. That's all we need to say. Just In this case, we loaded the CAR2PI coordinate reference system, that's what the CCRS stands for, and we tell it we want the Mercator projection. Now we add a feature to it, we want land filled in, otherwise it would fill in with a background color. Add a basic default coastline, all going to the AX object which came from the plot axis. Now, using that axis again, we add grid lines. I'm going to walk this through once. We'll see this repeated again, but once we get this done, we're done with this part. We can tell it we want labels, so we want the axes labeled with the latitude and longitude values. Then we also have to turn off two of them because the default from X-ray is to label all four axes, which interferes with the color bars and the titles. So we turn off the one on the right and the one on the left. Then we do the actual plot command. In this case, we just tell it to plot. Don't say anything else. We specify that the x-axis is going to be longitude by name. Y-axis latitude. Color map. Specify our VMIN values based on the maximum and minimum values of the sea surface temperature. And here's the transform that we need to explain a little bit about, because in this case, the data coming in is unprojected. It's on just a basic cylindrical projection of longitude, latitude values. Now, CAR2PI is going to take care of taking that data, reprojecting it, and then building the screen, the image you see here. Everything in here, the color bar is automatic. The titling here with the model time is automatic. The grid spacing is automatic. If we want a sub-region, think back to that tripolar grid. One of our biggest problems for the longest time playing with MATLAB is it's hard to do this because we have a non-rectangular grid. It's a curvilinear in the northern section. You spend a lot of time finding your X and Y values for where you want to pull this at. That's going to be a pain. In particular, when you're working for something like, in this case, I do need to mention that when I specify the Hawaiian longitudes, I specify them on a -180 to 180 projection. To convert that, a quick side note, you need to do some modular math. Python has a percent sign to do that, and %360 does the conversion between the -180 to 180 and the 0 to 360. But what I was trying to get at is they have a where function. This is somewhat new. All of the numerics we're doing here are NumPy arrays. NumPy doesn't have this. NumPy has you can locate conditions, you can subset. But this one has a very nice capability that all I need to do is say, I can specify my latitude and longitude values. I have to do that percent thing because I'm specifying on the -180 to 180 environment. Then I add drop equals true. Now that's important because without that, I'll simply get the full array back with the values I'm not interested in mapped out, but it's still a full array. If I tell it to drop it, it dumps them, and I come back with a much smaller data set. And we're going to go ahead with a plot and Mercator again. Same as before, most of up here you can ignore because I haven't changed anything. All I changed down here a bit is I gave it a command to plot, but this time I wanted to plot a contour, a tilt contour. Same arguments as before. I added level equals 20, let it automatically choose 20 levels. I'm not particularly interested. I wanted a color bar added to it, and the transformers. And that produces a nice clean file like that. Very simple, just a few steps. And that's pretty much it for NetCDS. We'll do it on time. Okay. Grids typically are a little bit more complicated. I'll deal with the complication. The plotting is very straightforward. We have four options, pie grid, X-ray again, if you have Pinio loaded. I don't. Pinio itself, or you can do the roundabout way of going back and using utilities like wgrid2 with a Linux utility for reading and writing grid files, or CDO, climate data operators, convert your grid to a NetCDS and proceed as in the previous example. I'm going to go with pie grid. And I'm going to read a wave watch 3 data set, plot the parameters, significant wave height, and again, we're going to take another look at Hawaii. The pie grid library can be installed the same way the X-ray library is, with a few caveats. It does require some extra software. We begin by importing the libraries. This is the same as before. The only difference here is I added PyGrid and NumPy because I have to do some work with the numerics directly. We're going to begin with opening the file and display the contents. thing to note here, grid files are different from NetCDF files. NetCDF file, you open it to get the whole thing. Grid file, you open it and you begin going record by record through it. You have to iterate. You have to loop through all the records to get them out. It's very similar to buffer in that respect. You'll see that in a bit. Here we open using the pygrid open command. We give it the file name. This is a wave watch multi-1 global 30-minute data set nowcast. That's what the F000. Pygrid opens this, loads it into the grids object. Now I have to iterate through it to take a look at what's there. I could simply index 1, 2, 3, 4 and just say grids 1, grids 2, grids 3, and so on. But I can do this and get it all at one go with a simple for loop. Loop over all the grids, and then print out each grid value, and it goes off the screen here. Gives me a lot of information I don't need. But the one I'm looking for is number 8 down here, significant height of wind waves. Now, significant height of wind waves in the basic printout doesn't show me the short name. That's the long name. You can reference off of that, but you can also go and dig a bit further. There's ways to get that information out. And so you can select with the long name. You can select with the short name, the abbreviation. You can select with many other keys. You can get all the forecasts if you have multiple forecast times. You can get levels out of it if you have levels in the file. The select method returns a list even if it's just a single message. Now here, this is a little different because we're calling grids as if grids was a function, but we're talking to an object. It's not a method, it's built in, it's part of the grids capability. If you hand grids a short name or any other parameter name, forecast time, or whatever I wanted, notice I'm not using double equals. This isn't a test, a logic test here. I'm handing the value for it to compare. And that comes back, loads it into the list. The final bit on the right is indexing to the first message that comes back. Python indexes from 0. There's a lot of information in each grid record. This only shows a small fraction of all that information that comes flowing in if you take the time. There's keys in the grid object. This is one grid message. Each grid message carries this information. If you plot this out or take a look at the notebooks from the website, it goes into detail. All these different things I don't want to. The easiest way to get the information the data we want, which is latitude, longitude, and the data field itself for the significant wave height, is to use the data method. Just so. Data, comma, lat, comma, long equals the object name, swh.data. That's all you need to say. This is a neat feature of Python. It's able to do multiple assignments from a single command. So in this case, it's bringing 3 arrays back with one call. Now we proceed as before. This begins to look similar now. Except here, SWH isn't an X array. It's a NumPy array, and it doesn't have all that plotting hardware or machinery attached to it. So I have to do some of the lifting myself. I open the figure, I set the axis up, I call the plotting right off the bat. T-color mesh is a surface plot. MATLAB has one called just T-color. Longitudes, latitudes, data are passed in with the color map, and I specify the transform. The rest is pretty much the same, other than adding coastlines, grid lines. Beyond that, it's the same. And it produces the plot like this. Let's move on. If you look at the data itself, this is a masked array. We specify the data using the type, the built-in function. Now, NumPy masked array is a little special. I just want to talk really quickly about that. When you're dealing with oceanic data or any kind of global data or any data where you've got big gaps in the data, land mass, ice mass, whatever, you have a lot of problems dealing with that mass. You can typically delete the data by multiplying nans to the appropriate point. Now you've got a lot of nans to deal with, which can throw off your statistics. NumPy masked arrays has 2 arrays, the main numeric array and a matching Boolean mask. And the Boolean mask can be flipped on and off as you go through. It doesn't matter. It doesn't affect the original data the mask you saw. You can actually take 2 masked arrays and do mask map between them, combine masks, subtract masks, whatever you want to do, and you'll see that it's immediately reflected in the data without touching the data.
Does it overlap the mask? Then does it affect the mask?
You can. You can make a multiple. You only have one mask per. But if you have 2 objects, you can pull a mask from each one, play with them, and apply them to either of them. We do this frequently when you have multiple sets, and one has a bigger ice field than the other. We want the overlapping overall ice field, so we can multiply the 2 together, combine it back in, and we've covered all cases. This is how, using the data method, which we just used before with no arguments, you can use the same data method to subset. You just simply have to give it the latitude, longitude limits. very similar to where, when the data comes back in the same last line, formulation, and we can plot it just as before, except in this case, I'm doing a contour. So a contour like we did before, but I have to call it explicitly and give it the latitude, longitude, and data information. So, moving very quickly on the buffer. Buffer is the odd child here. It's also the newest one for this. We didn't, until recently, we couldn't read buffer with Python. We had to go through bufferlib, which is the library maintained here for reading and writing NCEP buffers. NCEP buffer is a new set of wrappers to bufferlib. So when we call it in Python, it's literally calling the fortran underneath that. We're going to work with I went a little quick there, but I want to mention that the buffer files themselves here are special. They call them data tanks. And this is all the observational information the models need to process. And these tanks are large, rapidly moving processes that I just pull a snapshot. The only difference here is we're importing NCEP buffer. Everything else is the same. What I've actually done here to read the file is I made a snapshot of this particular tank. It's called the XX005 data tank or buffer file, and made a copy on my local system. It's Argo. In that long, complicated thing here, we've got a large array of Argo floats drifting around the world ocean, over 3,000 of them. And they're surfacing and submerging on about a 7 to 10 day cycle. Every time they surface, they transmit their information back, and they get temperatures and salinities and depths. Here, all I have to do is call NCEP buffer, which I imported, with the open command, give it the name of the tank. Come back with an object called buffer, just like that. Movement and data access within the buffer file is not that, it's sort of like PyGrid, but not exactly. PyGrid, you can just simply index through like it's a list. Buffer, you have to give it the physical commands, the advance, load subset, read subset, you have to rewind it, and then close it. They can do many other things. There's checkpoint capability. You can move directly to points in the file. You can pull out all sorts of capable data based on multiple mnemonics, printing and saving, so forth. But the one thing to keep in mind is that because it's bufferlib underneath, bufferlib is unforgiving. You make a mistake, it doesn't drop you out of your scripts or your routine. It drops you completely out of the interpreter all the way back to your command line. Proceed with some caution. We open the buffer file. Now we issue an advanced command. It returns a return code of 0. We have to load the first subset. Buffer files are arranged in subsets and replications. A subset is one observation, considered a profile or a station report. It could be anything coming off a meteorological station, a balloon loft, anything at all. In this case, we're looking at an Argo ocean depth profile. We're going to pull out the very first one with a load subset command. Okay, I just want to mention here, it's verbose. If you print out the entire thing, it's huge. It's about a gigabyte of data in one small file, one small tank. In this case, these are all the headers in the beginning of it talking about the instrument. The instrument is an S2X type of profiler. This is the serial number. Main thing we're looking at is the water pressure down here, seawater temperature, and the salinity. Those three, you can pull the data by just simply saying read subset. We load it, now we read it. I have to squeeze that using a function, a method for the NumPy array that it came back with to get rid of the extra dimensions. I convert it from Kelvin to Celsius. Do the same thing for salinity. It comes in PSU units, I don't care. Depth comes in by reading the water pressure mnemonic, squeeze it, divide it by 10,000 to convert it from Pascal to water depth in meters. Pull the longitude, latitudes, and I can get the date and the receipt date. Buffer stores everything as observational related. We want to know when the observation was made in the field and when it hit our tanks. And then you close it. Now we set up the figure. This time I'm going to play a little bit, and I hope I have time just real quick on this one, because this is kind of fun. Temperature salinity profiles. We rarely consider them one without the other because they're both related in the ocean. In this case, they want them both on the same plot, sharing the same depth axis with different x-axis for each of the values. I begin by setting up the figure. I set up an axis here and label it AX1. Then I plot the temperature against depth. Now, it's XY, temperature is the x-axis, depth is the y-axis, give it a red line. I set up a grid. I invert the axis. I'm an oceanographer. We tend to like our surfaces at the top and go down in depth. Then I tell it I want a second axis using the first axis and twin. That's what twin y does. I'm twinning off the y-axis, sharing the y-axis, and now it's sharing the x-axis, or allowing me a second x-axis, directly addressable. I plot on AX2. There's a bit of a clue joint here. The second plot command is the one that does my salinity. The first one just simply puts a blank plot in, but it labels it. So that when I put one legend out for one axis, I get temperature and salinity on it. I'm plotting them on different axes. They would have different legends associated with it. Plot the legends, set the labels, make a long, complicated title string that just talks a bit about it. So it has profiles, and there's a latitude and longitude extracted from the data set, and the timestamps and the received timestamp. I use subtitles to put a title above that second x-axis so it doesn't interfere. So, I covered a lot of ground in a short time.
Negative 4 minutes for questions.
So, you'll have to speak a little faster than light, but I think I can manage it. Are there any questions on all the stuff that I covered? I don't know.
Specifically about the plotting, why can't they share the same y-axis?
You can. But we do share the same y-axis. I had one y-axis for two x-axes.
But you had twin. Oh, that's just
Yes.
the reference.
I'm twinning off of the first one, using the y-axis as the share point, and produce the second x-axis.
Right.
Now you can do it the other way. You can twin off of the x-axis and have two separate y-axes. And you do this frequently when you're putting your information, you're doing a standard PS plot. You share the x-axis because you want a time series typically. Because you want to plot two different things and have one axis deal with one line and the other axis deal with the other line. So it's the same thing that's changed from twin x to twin y.
And I know MatPlotlib is very MATLAB-like.
That's the name actually hints at that. It's MatPlotlib. It's MATLAB plotting library. They, when they wrote it, modeled it after MATLAB's system. It was one of the first fully interactive graphics packages out there. So, in fact, within Matplotlib, there's a sub-library called PyLab. And PyLab is fully interactive. I don't want to get into the subtle differences, but it's actually extremely close to MATLAB. It's easy to transition between MATLAB and Matplotlib.
If I prefer R, if there are...
I think it's going to be the last question.
Okay.
Oh, that depends on your Python distribution, but yes. The simple answer is yes, there are. I'm actually running this off of a distribution called Anaconda. That's available from anaconda.com. Free, widely, very, very common. I think Canopy also has it, but Anaconda supports R directly from Python. You call R from Python, Python from R. You can actually mix the codes together to do that. That can make it really complicated.
Okay, we have to move on to concepts.
Okay. Go.
I have 3 parts, and the first 2 parts are pretty much the demonstration. Okay. So, I am working at the Hurricane Project team, and we have 2 couple ocean and hurricane model systems. One is HWork and the other one is H1. And then what I'm showing here is mainly focused on the regional, because of those systems are a regional model, and then, pretty much running for 5 days forecast. So dealing with a very short and a smaller region. So what I'm showing next slide is mainly in an example of what I produced in terms of graphics. So this is animation of a model SSD and the cooling every 6 hours for Hurricane Lane, which it just hit Hawaii, and then I'm particularly looking at 0 cycle in August 22nd. And then this one is the animation every 6 hours at the 10-meter temperature on the left side, and the cooling, SSD cooling from T-colon 0. And on the left panel, you saw in the ocean currents as well. And the black curve is the predicted hurricane lane track, and the dots are the instantaneous positions. So you know, from what I see here, you can tell, you know, the SSD cooling due to the hurricane lane is about the maximum 2.5 degrees. And then, you know, on the left side, you can see, you know, storm-induced internal waves at the surface and interacting with the warm core eddies on the ocean side. So it gives a lot of information you can make up, right? And then the second slide. So this one is I'm going to show that the animation of a temperature along the predicted track for the same cycle, for the same storm. The vertical dashed line is storm center. Again, this is every 6 hours, changing it, and then the temperature from 0 to 350 meter depth. And then I contoured every 1 degree. And a solid line is odd number, and then dashed line is the even numbers. So right now you can tell that is all the cold wave generated after storm. So before the storm passes, the temperature is about 29 degrees, and then during and past the storm, the temperature goes down to 27 by almost 2 degrees differences. And then not only storm impact on the upper ocean, and also in the subsurface as well. So now, part 3, what I'm going to show here is sort of producing more, journal publication quality of graphics. Right? In a MATLAB, you can use a graph. Oh, the quality is horrible. So a MATLAB is expensive. About the 2,000 basic case price is $2,000, and then if you add the number of tools, it goes in a few $1,000s. So, but Python itself, it's free. You can produce a quality, very high quality graphics. So what I'm showing here is that predicted track intensity in the bottom panels for the maximum on the left and the P minimum on the right side, and the blue in predictions, and the black dot representing in the best track data for hurricane rain for this cycle. So I'm going to briefly go over this particular script to generate this graphics. All right, so I'm using a subplot. Let me see. Before I go on, my Python script is called atcf2bt.y. Sam has gone to do how to run the Python script without having this 5 words after this Python script. But what I did here, these 5 variables, I put it out as an input argument because they can be changed with each cycle and each model system. Here I use HMON. You can use HOF, and then this is experiment. It's here, or you have a different experiment, and the TC ID varies from 99 to something, and then hurricane name, TCID name, and this is a cycle. So I'll put those variables outside of this Python script so that we can continue use the script for different cycles, the storms, and the systems, and the model experiment. Okay. So once I use the input argument, how does this HTCF2BT.Python script get defeated? So in this order, right, the first argument goes into the internal variable model, and the second one, I put it in M20 and put it into XPT0, and the TCID, third one is the 14E, goes into TCID, and then lane, and goes into the storm, and the cycle, capital YMDH. Right. So these are all the internal variables inside of my Python script. Okay. Now, going to the figures. So what I highlighted here, in fact, Todd had shown already, but he didn't point it out. But I'm going to point it out here. So I am using Matplotlib library, which is imported as a PLT, and the figure I decide. And then here, figure size I define. Here, the 11 by 8 inches. Okay, so it is inches. And Todd example, he put it in DPI 100. It's a more like quality of the resolution of the graphics. Here, I just using default resolution, but I set the physical size of the figure. And here, use the subtitle, which is the figure title. This is different from the plot title. And so I'm going to show you plot title later on. So this is pretty much subtitle gives you the title of that particular figure, which has the three plots. Right? So now top panel, if you recall correctly, so top panel is mainly track plot. So I decided put it in AX1 equal to plot, subplot to grid. So this is number of ways you can do the subplotting, but I'm using subplot to grid, right? And the first parenthesis numbers is 2 rows and the 5 columns here. Okay. So if you recall correctly, the graphic that I showed you is just only 3 panels, right? But I used 2.5 subgrids because I'm manipulating, okay? So, and the second parenthesis shows that the top row, which is 0, and the second column, second grid that I'm using, right? And span over 3 columns. In other words, I have 5 subsets, but I'm using first one and the second, third, and fourth, right? That's what I'm doing it. So now I'm plotting the next line is the best track, best track in black and the dots, and the marker size is 2. So you can play with the line width here and then the size of a marker. Followed by predicted storm track and the different color, which is B, and then different sizes. Although in this figure I use the base map, which will be done for Python 3. In other words, I use Python 2.7. And if it is gone, you can use a cartography that Todd has shown, or you can simply, bring use some your own, set up your own subroutine in order to get the, coastline. This is what I did here. And this one is setting up the figure current axis domain. And the 100 varies from 180 to 220 degree west, from 5 to 30 on longitude. And then I put it in grid. If you don't put it in, you don't see any dotted grid lines at all. It's just default. And then plot title. This one just put the title on this particular panels, right? Okay. Next, the bottom left, which is a B maximum plot. So it has two layers of plotting here. So first one is let's just say the first one is a subgrid here. Instead of using 5 earlier, I used 2. Okay, so this is the bottom 2 by 2 frame, but I'm ignoring the top panel. It's already done the top panel, and the bottom panel here I'm using it bottom row and the first column. That's all I put it in. Okay. These two lines is again test and then predictions of the P maximum, and what on this particular line is my own plotting function, right? So, okay, now I have my own function is called the plot underscore Stafford underscore Simpson underscore WP scale, and I have the input argument is Vmax. So what this one does, plotting these 6 lines here, okay? So TS in science, category 1, 2, 3, 4, 5 at different categories. So that's what this one does. And here I plotted an legend. Okay, so this legend is associated with this WP scale, Stafford-Simpson scale. Okay, the reason is that if I go up there later. Okay, so this my own user function, which is called plot Stafford-Simpson WP scale argument, is like this. But inside, it's calling another function, right? Called Stafford-Simpson. Okay, so this is my own function composed with a dictionary on the left column and the P maximum in the list. The first column. Second one is the P minimum, and the column on the last column has 5 different dictionaries. So in order to call this function, I have to type from util or hwork import this particular function in here. Okay, so that's what you have to have in the beginning of your script. Well, it can be done in the middle of script as well. All right, so this one is when you call them. I'm not going to go to this one. So this is the P minimum. Oh, I'm sorry, I have to do it. Because I pointed out earlier, plot legend for the Stafford-Simpson wind scale. Here's a legend of labels is coming from this side, this one. Okay? And the P minimum, I don't have a label to specify. And whenever you want to call the plot legend for associated with P minimum, you're not going to show it because I didn't specify the label here. Okay, now both P maximum and P minimum panels plot. What x-axis is the date. Okay, so this is particular treatment. Requires particular treatment. Okay, so what I'm using here, I'm using the matplotlib library date, and the class is hour locator. So I put it in range from 0 to 24 every 6 hours. The reason I put it in 5, when you do NPA range, if you put it in 24, it doesn't come 24. It just only goes from 0 to 18. So I have to add extra, numbers. And the date format, okay, so we put it in the format is date. It's a format. And then the major location, I'm going to put it in every day. date locator, and the minor locator is going to be hour locator. Every 6 hours, and the format is only day. And overall, you're going to have this is month and the year. Okay. So month and the August and the year and the each days, and the minor takes is every 6 hours. And then I'm repeating again, this is about right for P minimum, calling my own function, and this one is a subgrid 2x2, and the lower right corner of the panel. That's what it does. And then I'm repeating x-axis 4 times in red boxes. And then now, on the top panel, I put it in the lesson in a different locations. Okay, so plot lesson, so I'm putting this box is outside of the panel, and the location, X location is 0.90 and the 1.70. Location is upper right, and then for the axis pad, I put it in 0, and then you put it on, it determines the font size here. And then in order to save the hard copy, you give a file name. You can do any images files, PNG, PS, TIFF, and then TIFF, anything. And then command is plot.save figures, and it gives them a name. Now on this options on the right side, you can do whatever you want. But in a particular box inches, height means you're going to give it a white space around the margin side. And the pad inches, get rid of all the,
Are these padding inside each subfigure or inside the entire box?
Entire box. Yeah. If you want to do the pad inches in individual panels, you have to use different subplotting, which is axis grids or some other options you can use. Okay. Now, to display the figure on X windows or any figure windows, just type plot shell, and you ended up getting this figure. Okay, thank you.
Any questions?
Any questions?
Oh, we did have one question. Sorry.
Good, all right. So usually say, I remember the figure size as 11 by 8 inches. That's how to save, that's how to save into that. Yeah, physically save it. Yeah. Yeah. So when you save the figure, you don't need to touch it, because when you start to plot it, figures give the size in inches.
You can override any of those options that you want to work with them and specify what you're doing. It's a combination of your figure size, your resolution. Are you going to like a page format, PDF, or are you going to have a PNG?
Yeah. Yeah.
Just at the beginning of the presentation. Each of them did it a different way. Yeah. In fact, that's one of the things about the plotting system. It doesn't constrain you to it in any particular way. Either multiple ways. And you will sometimes find that on the fly you create the figure, and you want to make a large version copy of it and a small version copy of it for a web application, something like that. You can do that without having to change anything on your figure size. Tweak a few parameters on the layout.
There's
Oh,
a
what was the
question.
chat question? I want to see what that is.
Input array and other is not working.
Oh, okay. We have a question in the chat. I hope you can hear me.
X-array.
X-array. Now, if you try to import X-array and you haven't installed it in your distribution, you're not going to get it. This means you have to, if you're working from Anaconda or Canopy or any of the major Python distributions, there's usually a package manager that comes with it. If you're doing build your own, which you can do from Python.org and use something like pip or easy install, which is not recommended, you have to build these things yourself and install them. All the stuff's available online for free. The level of complexity involved in building some of these modules can get pretty high. Most people, what they do is try to find a distribution that comes with a whole bunch of stuff under the covers without you having to deal with it. Anaconda comes with X-ray built in.
Hi, I'm Diana Spindler. I'm also part of the verification group here at NCEP, and I work mostly with the WaveWatch 3 spectral wave model. Now, as a scientist, when we have these models, we like to monitor them. We like to see how well they're doing, why they can be improved, and if our improvements actually work. To do this, we generally end up spending time gathering data from various different places, in different formats, perhaps over different time periods and different areas, maybe different variables. We have to put all of these things together. To be able to compare them, we have to put them on the same basis. We spend a lot of time trying to collocate our data into the same time or spatial parameters. Now, Python has a nice library, Spacebar, but Spacebar is not working. So, thank you. So, in Python, we have something called Pandas, and these are not the black and white, roly-poly little animals, or rather big animals. This comes from panel data. It's an open source library for tabular data manipulation. Now, in scientific data, we're used to matrices, but we're used to matrices of numbers. Tabular data allows you to have one column where you can have your scales, minutes, seconds in one column. And you can have your next column, it's going to be a string. Your next column is going to be an integer. The next column could be floating points. It doesn't matter. You can have all of these arranged on the same table. This is the strength of Pandas. So what does it do? It processes specifically looking at time periods and looking at these heterogeneous tables with all the different types of input. Depending on the data, you have different data structures you can choose. We had Pandas series, which are one-dimensional, so think of things like columns. Usually you think of vectors, but these vectors have indices, and it's not the usual index from 1 to n. These are actually indexing on time if you want it. You set your index. You can have two-dimensional data frames. This is where you think of tables or spreadsheets. Or you can go to three-dimensional panels, but usually once I leave two dimensions, I go to X-array. Because you can have a data frame of data frames, so you don't really need to go into panels. Now, remember I said you can have different data where you have subsets of your data are missing, or you have different regions, and you're putting it together in one data frame. Pandas will automatically fill those gaps with NAND. You can convert them to zeros, you can make them 999, whatever you want. But those gaps will be filled in so you have a nice, complete data frame. It makes it really easy to subset your data then. Whether you want to look at your buoys by location, maybe you want a region by laps and longs, maybe you want a time period, maybe you want to look at all buoys for one day. All of these manipulations are very easy to do in a Pandas data frame. Once you have your data nicely subsetted and you have it right to what you want to actually start working with, then it integrates well with all your other Python libraries. So now you can go into stats models, you can go into SciPy, you can bring all the different tools to actually work with what you've got. And then once you have your results, it's easy to load them to a database or import it back from the database if you want to keep a long-time series, for example. So this talk is going to be a very simple example. I'm going to be showing you how to use Pandas data frames to validate WaveWatch 3 model output at one buoy point against NDBC in situ buoy data. During it, you will see how to create these data frames from ASCII files and from remote data servers. Open that. Once we have our data, then we will play a little bit with selection, merging, and grouping, just so you see how this works. And then some very basic statistics, so you can see it can actually play with your data. This is a picture from our website that we maintain here, and you notice we do many different things. We've done it for many years. We do it for all the buoys that we have output. We do it by the month, so across all months, all the forecast towers, various different variables, different ways of looking at it, like a scatter plot, QQs, Taylors, or aggregated statistics. This talk is concentrating only on this first figure and these very simple stats. So first things first. This is Python. We start by importing the libraries we're going to use. Matplotlib for graphics, NumPy for your numerics, Pandas, this is what we're going to show here. Tarfile, Xarray, and NetPDF4 I use to import my data, and you'll see how I use that. And then from datetime and relative delta, I have neat ways of using to manipulate your datetime stamp, basically. Start first by choosing a buoy and the period of interest. So I'm going to say buoy ID 41008 for the year, this year, month 6, June. To get the quality controlled NDBC data, the URL basically for NDBC, for the quality control data, so this is data that's more than 45 days old, you just have the buoy ID and your year, and it's an PDF file. As Todd did, I'm going to use Xarray, and I'm going to use Open Data Set to read this URL. It's going to get me all the data for that buoy for that year, and it's going to decode the times for me. I'm going to select a specific month, because I don't really want the whole year's worth of data. So I'm going to start at year. Remember, I defined my year before, my month, and the first day of the month. My stop at is when we start at the beginning of that one that I just defined. Go a relative delta of 1 month forward. So it's going to go to the next month. It's going to go to July 1st. But I don't want the data of July 1st in there. I just want the data of June. So I got the first day. Subset the data to this time period, because now NC data is an object, it's an Xarray object, with a full year's data. So to subset it, all I have to do is select my time slice, start at the start at, and Xarray plays nicely with Pandas. It has a method called toDataFrame. So NC data is my object, I add the toDataFrame, and now data is a Pandas data frame that I can play with. To take a look at what did we actually get out of this URL, you can do data.keys, and you get all of these names. These are the names of your columns. This is what your data contains right now. Another way to look at it is to look at the first rows of the data frame. Data.tag will do that. It'll just show you the first few rows, but the entire data frame is actually there. You can see, if you can drag it, you'll see all the different columns of data that we got coming out of this. I like to index on a date time stamp, because most of what I do is time series. I want to see how the model is doing for a specific day through time. So I'm going to reset my index. So data is now going to have, remember I have that time column in it? I'm going to use that as my index. But this is a buoy that reports every 10 minutes to the hour. So it reports at 1:50, at 2:50, at 3:50. The model produces results on the hour. I'm going to round up that. I'm going to kick up those numbers to the hour. And I'm going to give my index a name called datetime. And that's what it looks like. You see now datetime is my index. It has the year, month, day, hour, minute, seconds. The original time was on those 50 minutes. Now it's been rounded to the hour. I can pull this over and you can see the entire thing is still there. But now it's nicely set up with my datetime index. The parameter names are long though, and they're all those columns that I'm not going to use. So I'm going to fix that. Here, Whenever you see curly brackets in Python, this indicates a dictionary. And you can join the meaning of two different things. The first one here is the column names that the file knows. These are the names it came in with, and there's the long names. The second column is the names I'm going to call them, just short names. Drop keys, this is a list interpretation intended fun. Remember I did data.keys to see all my column names? So here, for a key that's not in my parameter list, I'm going to make a list of drop keys. Data.drop is then going to drop these keys along the column axis in place, because I'm doing it on my data object. So now my data object is going to lose all of those columns. And I'm going to rename my parameters. My columns are now going to be equal to my parameters in place again. So I don't want to keep all the old columns. Take a look at that. And now you see I only have 6 columns with the short names. This is my datetime index, every hour reporting. This looks kind of strange though. This is the peak period. It's in hours, minutes, seconds, and nanoseconds. Python, especially Pandas, treats nanoseconds in 64-bit integers. But my model reports my periods in seconds. So I cannot compare this, so I have to fix it. So, to fix it is quite simple. I just tell it my data.tt is in this type format, which I know from Python, and I want it as a floating number. And then I have. Suppose we want to look at the data from a specific column. We want to pull out, we're not talking columns and talking Pandas series. Now it's a different data structure. I'm looking at the significant wave height. From my data object, give me the column HS. HS is now a series. So quartiles, I want to be the percentiles from HS, my object, for the 25th, 50th, and 25th. Just to choose some numbers. I want to look at the min and the max. Now immediately, this tells me there's something going on that Python doesn't like. So let's find out what it is. Print them out, and you see there's nans in there. So my HS series has nans in it. So, let's get rid of them. Drop the nans. That's all I have to do. And this drop in a method belongs to the data object. So I drop them, I rerun, and then I have numbers. I can see. It's nice to take a quick look at data. Every time I'm looking at data, I like to actually physically look and see what did I get. Series have this plot method attached to them. So it's not a pretty plot, but it shows me quickly what kind of data did I get. And grid equals true, just put your grid lines on it. You notice all I gave it was the HS, the Pandas series. It knew that my axis was my time series axis, and it labeled them for me as a datetime index. Okay, so in the above example, we used OpenDAP-Server to get the quality control data. If we wanted near real-time data, we could do it the same way, but the only thing we have to do is change the URL, because the near real-time data is not kept in the year.nc, but in this 999.nc. Fine. So we could do it the exact same way. Oh, there's another way, and I found this out just last week. Unidata has been developing something called Siphon. It's a tool for accessing these remote data sources, and they have an NDBC one. So from Siphon, I import NDBC. NDBC has a method called real-time observations. I give it my buoy ID, and bang, it's a data frame with all the different data. Now notice those columns are different names, but that's easy enough to handle. So next, we need some model data for that same time period. In this example, I'm going to show you data from our internally archived monthly files at Wiki. And the reason is I wanted to show you a tar file and an ASCII file. And this is a very simple one that we have. Inside that tar file are all these individual files. There's one for the nowcast and then all the forecasts. Inside of these is the data the model produces for every buoy with all of these columns. So you have your year, month, day, hour, the wind speed, wind direction, significant wave height, and peak period. So just think many files with lots of ASCII input, columns of input. I start off by making a blank data frame. Pandas or data frame open close is an empty data frame. I'm going to load data into it. Remember I imported tar file in that first line? Tar file just opens my tar file. I don't have to uncompress it. Now it's going to walk through each of those members. The members were on the month and the forecast. Remember N000, N024, all the way down. So it's just going to look at the member name, get that member, extract the file in F, and then Pandas has read CSV. This is how you read ASCII files. F from your member file, from your extract file, names those NCEP columns that I had defined before, so it knows what to expect. Separation, in my case, I know the blanks between the columns. Use calls. Notice I don't have the two. You can skip columns. Use only the columns that you need to use. Skip initial space. I have a header, so skip it. And don't index. I don't want an index column in this case, because I'm going to make my own datetime index. I like my datetime index. Pandas has a toDateTime method. If you have columns of data with year, month, day, hour, minute, second, you can pass that to this Pandas toDateTime, and it makes the datetime for you. Just so. You don't have to have them all, but you can. You need at least year, month, day, and then hours, minute, second is optional. So, since I'm going to have it in my datetime index, I may as well drop those columns. Set my index to be that datetime column. And since I'm reading these numbers for each forecast, I need to keep my forecast so I know which goes with what. So I just make up a column called forecast. A forecast says one number, and Pandas will fill it in for me. Like Jim Silk did, you notice the range goes from 0 to 169. 0 is the first forecast I'll do. 169 because I want to go to 168. And it always goes to n-1, so you always give it one more than you're looking for. And then my interval start is 24 hours. I'm going 0, 24, 48, all the way to 168. And then all I have to do is close my chart file. And this is what I have. It's already a data frame. It's indexed on my time. I have my forecast. Now notice this is not the buoy ID that I was looking at the NDBC data, because this file has all the buoys that model produces output for. So I have a lot of buoys in this file. The timestamp is also every 6 hours. That's because I'm looking at specific forecasts. Your 0, your 24, we only produce the model 4 times a day. So our timestamp is every 6 hours. I want to make sure all those forecasts are there, because I know that file should have all the forecasts. Oh, first off, I have to subset the data to this set buoy. So we look at, and that's easy enough to do. I'm just looking at my W3 data object, where the ID is equal to my buoy ID, and I copy it. This copy is kind of important when dealing in Python. Whenever you have an object and you're using something of it like this, if you don't do copy, it actually links to your original object. So if you want that object to stay as it is, you don't want to mess with it, you use a copy. And if you really want to be careful, you use copy, deep copy. Deep copy equals true, because that makes sure that they're totally separate. Here though, since I gave it a separate name, I can use just copy. So what does this look like now? This has all my datetimes just for my one buoy ID, all my columns, and again, these forecasts only show in zeros. So now, let's find out in there which are my forecasts and which are unique, because these forecasts are Pandas have filled in that column for all the time period that I have 0 forecast. 0 was filled in. I just want 1 0. I don't want 5,000 zeros. So I give it the unique, and it tells me I have all of these forecasts in this data frame. If I'm interested in just a single forecast, I can easily pull it out. And this N000 will be a data frame containing only the 0-hour forecast. And it'll look like this. And if I want to verify that it only has the 0-hour forecast, I can do the same forecast but unique, and I see that it comes back with 0. So now, recall we had the NDBC data that looked like this, and it has hourly data for my buoy, the same type of columns, latitude and longitude. I'm going to make a copy of it and call it buoy, just so that we can keep separate what's model and what's buoy. That's all. I could have used data. But now I have my buoy data and my model data, and I need to merge them. And this is where Pandas comes in. So from Pandas, I use the merge method on my model object, buoy object. Last index equals true. I'm going to merge on my last index belongs to model. So I'm going to merge on my model indices and on my buoy indices. I'm going to give them suffixes of _n for model and _b for buoy. How equals inner tells me I want the intersection. So I want only where I have both model and buoy data. If I wanted to do outer, it would give me the union. Yep.
So you're using the left index, you're joining onto the left of that column?
It's using those two in my merge statement. So my left index and my right index of what it's going to merge on. And it's going to merge on the inner method of it.
So left index is kind of.
It's my timestamp in this case. My right timestamp for the buoys.
Okay.
So it's just going to find where I have data for both. But it's the index, not the keys or the columns. It's the index, the timestamp index. And that's what it looks like. And immediately you see we only have data every 6 hours because that's where the model has data. And there'll be many repeats there because if we do down here, you see you have your forecast, 24, 48, 72, all the way down. And you see all the buoy data has _b. The column names now have _b for buoy. And the models are _n. Only the model data had the ID column, so it's just left as ID. Only the buoy data had the lat and longs, so they don't get underscored. So the only time you see the suffixes is when you have column names in common. Again, if you want to pull out one forecast, you can, and you notice the forecast column goes to only 24s. Now, again, quick little plot just to make sure we actually are getting what we think we're getting. You define your figure, you choose your axis. Both now is my object with my model and buoy data merged. So from both, I'm going to pull my forecast equals 0, and I'm going to plot it on my axis. But the y, I want the significant wave height from the buoy and the significant wave height from the model. And then I want grids along both axes. And then it's done. I can take a quick look and just see how they're doing. This is just a quick and dirty way to look at your data, see that you really got what you think you got. So now we have both the model and the NDBC data in a Pandas data frame book. The keys again gives you the names of your columns. And we're ready to calculate some basic steps. So first thing, these are objects. Objects have methods. Let's see what methods are associated with these objects. You can do a directory of your object. This is my object name, remember. And it will list out. This goes down way off the screen. It starts with all of these underscores. Don't worry about the underscore parts because those are internal methods. We don't really mess with those. But I went way down the list there, methods that show up without any underscores. I want to look at them, and I asked for this by saying, for X in my directory of both, if it doesn't start with an underscore, print it out for me, separating it by a comma and a space. This doesn't help much, but at least you see there's a whole bunch of methods here that we can use. I'm going to just look at correlation here. And then there's something called describe. It seems interesting. So maybe I look at describe. So both, I pull out my 0-hour forecast, I do a dot describe. And what it does is it does count, mean, standard. It does your basic stats for each column of that data frame that you passed it. And that's kind of a neat way to just see a distribution of your data. Help is available. All of those names, what on earth are they? How do you use them? You can just do help and your object name, dot, the method that you're interested in. So that correlation method goes with my object. It contains my model and my GUI data. And I want to know what CORD does. And it tells me I can choose my different methods. I can choose the person correlation, which is the usual one and is the default in this case. So let's take a look at it. Suppose we want to look at the correlation precision for one forecast grouped by day. And here's where we start grouping things. So, first, from both, I pull out the model data that I want, the forecast that I want. Group by is a Pandas method, Pandas grouper, frequency daily. So all of that, I'm going to do a correlation with my box underscore B, my buoys website. This is called method chaining. You can do this to your heart's content. Be really careful because things have to be in the right order. But you can look at it to see, did you really get what you think you got? And you notice this is a series. There's only one column of data, but it has a daytime index. The daytime index is telling me my group by worked because I'm by day. That was my goal. So can I go back in this?
Yeah.
Left.
Yes. Thank you.
Okay. Now it's correlation. That, yeah, okay. So my group by daily is the important part here. And you notice I get my correlation by each day. Now you can do this in many different ways you want to. The usual functional way to define your parameter you want, the forecast you want. You can do that. So from model, I'm going to take both from my forecast equals 0, my HS underscore M, I'm going to copy it because I like that. I can do the same for observation, just pull off the buoys. So now models and ops separate. We can aggregate each data by day and grouping the data. Whenever you think of grouping the data, think of all those loops you used to have to make to chunk your data. We're looking at chunks. So I'm just grouping by day chunks. My odds group I do have on purpose because I need this. So these are my observations grouped by my frequency daily, and I'm going to keep that. If I want to calculate some basic stats, also grouped by day. Statistics, whenever you start, you're always going to have somewhere or other model minus observation. So I'm just going to define a diff equals model minus observations. My diff now needs to be grouped. So I group those by the same frequency. And if you want to look at it, you can do so by looking at the diff groups.groups. But this is a long list, so I'm just going to look at the first 10 items. And you see here, the groups are by day here. This column is a day. The frequency daily. These are your indices. So my first day, I only got 3 points, actually. And then the second day is 4 more, because 3 to 7 is 4. And 4 more for the next day, 4 more for the next day, which is correct for me because I know my forecast is 4 times a day. Yeah, 4 times a day. This is a very simple example. If I was doing statistics for real, I would be taking all the buoys for that one day. And I also need to square that difference because you're always looking at model minus size or model minus observation or model minus observation squared. So I take the square and I group that by day. And I can also count how many is in my diff group. When I look at stats, look at how many you got them from. So the IF now is just going to be my diff group, the mean of that diff group. And look at it, and it's by day. It's already all done. RMS is the square root of the mean of spread difference, grouped by day. Scatter index, here is why I wanted my observations grouped before and the mean, because RMS and bias are already grouped. They're fine, but I have to divide by the mean of that day. I can't divide by the mean of any other, other portions. They have to be the same grouper. And I divide by that, and I have my daytime index. So notice these are series. These are all columns. It would be nice to have a data frame of the statistics, because it's all for the same days. So, I define a forecast equals 0 just because I want to keep what forecast it belongs to. And I say my ag stats now, this is going to be my new object. It's going to be a Pandas data frame. It's going to have these columns: forecast, bias, RMS, correlation, scatter index, and count. And I give them what I just calculated. And there it is. Now this looks like something that'd be nice to keep around and keep adding to our few days type of thing. So, import SQL. And this is really nice because it's very simple. You just define a name for your table, a connection, and now this is my AgStat is my Pandas data frame, right? So AgStat q_SQL, give it a table name, a connection, if it exists, append it. This, if it doesn't exist, we'll create it the first time. And then close the connection. That's it. It's saved to a database. You want to read it back in later? Open a connection, tell it what table to read, tell it, in this case, I want everything from that table, and then close the connection. There it is. So it's really simple to manipulate data and to save your results when you're done. Thank you. Any questions?
Yeah, some of questions.
Is there any on
Oh, you didn't?
yeah.
I hope they haven't given you guys the impression that we only use Python for data visualization and statistics. Those are just the ones with the most interesting plots, and pretty much the only ones that you can run on a desktop machine. We also use it to automate our large model workflows, but we didn't have a supercomputer handy for doing that, and it takes hours to days to run those things. It's a great glue language for all sorts of things.
Any questions about anything you've heard this afternoon?
Yeah, Bufferlist and WGroup2 and all the utilities that we went to are available from the NCEP website. You have to kind of search for it. I think I should go to the front door of NCEP. You can get to the NCEP central operations. They manage a lot of stuff.
Well, I don't manage Python.
No,
I usually come from developmental test bed center.
Python is very good. Yeah, and actually.
They repackage ENC's unit and distribute it as nice, usable Python libraries and the like.
I have a question.
That's available through their website. You go in the original slide, step back.
I didn't give this information out to everyone.
Here.
So come on, go away. I don't want that, yeah. I know. I'll get in there. If you just go to there.
Polar is our internal, or it's our web server for ocean-related stuff. And I just created this page the other day just to give us a single spot to store it and to present from it. It's available for anybody. You just go to the URL, which is polar.ncep.noaa.gov/. down the emissions for where we are. NGMMS, the NOAA General Modeling. There.
Wherever
we are.
Okay.
No, it's actually what we're doing.
No, I general modeling meeting in Facebook.
And
That's so nice.
all of it, okay, if you click on any of the examples or not LibreOffice, you need LibreOffice as well, but the examples, if you scroll down there, click one of the examples there and then click on the title, it bounces it through an external server maintained by the Python.org group called the Jupyter Notebook Viewer. These are the actual notebooks we use to create this stuff. All these notebooks, this is a form of Python interactivity that's fairly new and it's become extremely common. People are taking these notebooks now and they're generating data science work out of these. They're distributing them internally, externally. Netflix uses these notebooks for their internal logging systems as they're running. So they generate these notebooks that can use them. It's very sophisticated. But what you can do is go to that website and back up again. Go to the website, scroll to the bottom. There's a linky on the bottom there to the RSVP site. You can't get to it from here. Unfortunately, our internal Wi-Fi doesn't allow us to see.
We'll have our own website.
No insecurity. Outside of here, when you link in, you can go to the FTP server and pull down all the notebooks for all the examples. You can pull down the data that they looked at, put it on your local machine, and assuming you've got a Python installed that understands Jupyter, you can run Jupyter up as a local server, talk into it, open up a browser, and then play with the numbers and play with the graphics. Everything's fully interactive. Some publications online, some scientific publications are actually accepting Jupyter notebooks along with the Word doc for publication, so they do not only have paper, but you've got the worksheet that all the figures are generated for the paper, so you can work with the figure data. Yes, it does. You make PDFs, you make web text, produce slides. This one is a slide using a system called Reveal.js, which is a new slide presentation package. It's very powerful, and it's free.
Other than this small example, do you have any archive or storage that is some much broader examples?
Not in an example format yet. We have been generating thousands of lines of Python. We're beginning to use it much more now in the verification field because it is very flexible.
If you're looking for scientific data in general, there's a lot of tutorials online for that stuff.
But for more aspects of data and
Nothing.
We have some examples.
We have examples. For example, I use Hybrid, I use NCEP buffer, and I mentioned NCEP for Python. These are all NOAA products. And if you go to the search Google on Hybrid, there's a lot of places that are using this. The original website where they distribute this has examples and use cases. Most of this is something where you'll find people will take some of these modules, load something up they like, they'll load it up to, typically up to a place called the Python packaging, Python, known colloquially as the cheese shop, if you want to find Python. That's the big repository for Python modules. It's a public, open, licensed, open source. You go up there, you can install any of these modules into your local distribution. That's the most common way of doing that. Not depending on any particular flavor of Python. You go to Python, if you type in there, you just type the P, Python, PY, that's PI, that's the word. And that's the front door to the packaging. That's where we get a lot of our stuff. We also get a lot of our stuff, if we come pick a distribution like Anaconda, which has its own large repository of software. You can install any of those as well. Probably not. But,
So, for those on the phone on the WebEx who missed all of that, you can check out our website. Where did it go? Yes, this is a website for the presentation that we just gave, You can see all of our presentations as well as some example data that you can use to reproduce some of this.
I have a question about Python. Is it difficult to write it? Is it a difference in Python?
I've never tried to use it.
It's not really difficult. It's mostly a case where if you build a pure Python application,
So the question was if Python is hard to use.
and you look at it, you'll run it, it's an interpreter, it's slow. They have a lot of profiling software available.
That's for Python, not CPython. Python is the Python to C converter.
No, that's actually very easy to use. You have to go through the documentation. Typically what you do is you take your existing Python, put a few decorators in it on the certain lines, the areas, the definitions, the functions that you want to translate into C. And then the Python will take that and convert it into an executable that will run in the place of your regular Python. There are translators for C. There's a Fortran translator, F2Py, that'll do the same thing. If you have a Python code or you have some Fortran code, you want to make it Python compatible, you add a few decorators that comment for Fortran. So Python, they're indicated that this is not going to hook to your Python. Take your Fortran utility, compile it with this, the Python interpreter picks it up and runs with it. Now you can call your Fortran from Python directly, and it comes back in as a data structure or NumPy variable, whatever you define. So to be clear, it goes both ways. So you can make your Python into Fortran. If you wanted to, you can make Fortran and Python. There's a lot of interoperability on this. And there's Number, the third one that I mentioned. Number is a new one. And that doesn't require recompiling. You actually add a single line ahead of your function that tells the Number system to pick up that function, translate it using LLVM, low-level virtual machine. It's a new high-powered compiler. Instead of doing like a C compiler or Fortran compiler, it takes it straight from Python down to machine code and executes it in its place. It's very fast. DARPA got so interested in it when the company is actually an Anaconda product. And they gave them about $12.5 million to continue development of this thing. It is a very fast speed up if you have the right kind of pure Python bottlenecking. You want to make it faster. Other questions? Thank you very much.
All right, thanks everyone.